Hello and welcome to our DFT webinar on steam condensate. My name is Ari Bregman and I will be your presenter for this webinar. Regarding the presentation today, I ask that you submit your questions either online, either during the webinar or after the webinar. I will be answering all your questions by responding via email to each and every one of you. We're also going to be recording today's webinar, and that will be available at the DFT Online Resource Center, which you can see the address for that on the screen that you're looking at right now. Today we're going to be discussing the uses of steam. I'm actually going to start with a brief history of steam, moving into problems that arise with steam systems, and then get into some solutions as well as valve applications within steam systems. I do like to start with the history of steam because I think there's a lot to know and understand there. And you know, in terms of the industrial world, steam is kind of a new means of providing energy to the industrial world that we know today. So without too much further ado, let's get started. As I said, I want to start with the history of steam because I find it quite interesting, and it does go back a long ways. When we think back to the beginnings of the Industrial Revolution, all the factories were located on streams where we could take advantage of the swift-moving water to turn water wheels that would drive shafts and eventually drive all the machinery that was located in the factory. That meant that the factories all had to be located near an appropriate stream, or a dam would have to be created to create the potential energy of a reservoir of water to be able to drive the water wheels. Steam changed all that. Back in 1698, Thomas Avery designed and patented a basic steam engine for use as a mining water pump, and really developed the first industrial use of steam through that little engine that you see on the right-hand side of the screen. That was over 319 years ago, and things have changed a little bit since the end of the 17th century. Thomas Newcomen kind of refined that steam engine a little bit and used it for dewatering the deep mines in England that were around during that time. And it was 1712 that he created the steam engine that you see with a little fire at the bottom, creating boiling water, driving a piston that would cause an arm to move that would raise and lower the pump rod that you're seeing on the left-hand side of that steam engine illustration. James Watt is a name that we all know very well. He used a steam engine to drive a big wheel and created the first steam locomotive back in 1778. So now we're getting to the end of the 18th century. But this was a great boon to the Industrial Revolution, facilitating the transportation of the output of all those factories to other areas of the countries in which they were located. This allowed factories to get bigger and bigger, and of course they were selling their outputs to a bigger and bigger market all the time. These steam engine inventions all were developed in England, as I said, back in the end of the 17th through the middle of the 18th century. And they were really helpful in launching the Industrial Revolution and creating the foundations of the industrial world as we know it today. But a lot more has happened in the last 200 years, and so let's move our time machine forward a little bit, and let's talk a little bit about all the different industries that use steam today. As you can see from these illustrations, we've got chemical processing, we've got mining, we've got different petroleum production, refining going on, power generation. The list is quite lengthy. And most famously, of course, power generation is the industry that we might think of quite a lot as the main user of steam in our world today. Without steam, a lot of these industries would not exist in the form that we know, for sure. So how is steam used? Well, there are two main ways that steam is used in all the industries I just described. One is, of course, transferring heat into a process. The second way is to create work, for example, to drive a turbine to generate electrical power. So why choose steam as your medium for transferring heat or creating work? Well, I guess all these answers are probably about as obvious as they seem. Steam can be very easily generated, plus it is easily controlled and transported. It really is an ideal medium for heat transfer, and because water is so abundant everywhere on our planet, and heat sources or the options for heat sources are so numerous, it's really pretty easy to create steam. By managing the temperature and pressure of the steam, we can also use it to do a lot of work that powers the world. So the bottom line here is that because water is everywhere, and there are so many options for heating that water, for instance, coal, natural gas, nuclear reactors, the list goes on, you can see why it's easy to make steam and it's easy to use steam. As you can see on this slide, the top three industrial uses of steam are power, pulp and paper, and chemical processing. Within the chemical processing industry, steam is applied to a wide variety of different applications such as automation, quenching, dilution, fractionation, mechanical drives, and stripping. These are just a few of the ways that steam is used just within the chemical processing industry. In the mining industry, industrial steam remains in very common use today in a broad range of applications. However, the deep mine pumping or mine dewatering, although still being practiced today, is practiced quite a lot differently. We don't use steam necessarily to drive pumps directly. We might be using the steam to, for instance, create electricity for cogeneration in the mining plant, or steam may be used as a heat source in the processing of the ore that's being mined. So the uses may have changed, but steam is still very, very important. Companies in the petroleum production and refining industries use steam for many of the same processes used by the chemical industry. It's common to see steam used for dilution, fractionation, quenching, stripping, as I mentioned in an earlier slide. But steam is just a very common and safe source of heat input into the process. And that process, of course, is refining the crude oil into the subproducts that we need and use in our everyday lives. The power generation industry relies heavily on steam power, and with the exception of most of the renewable resources that we can think of. Some of the solar processes are also using steam, creating steam by using mirrors and arrangements like that as the heat source to convert water into steam. So beyond just the photovoltaic cells, steam is also a common way to drive turbines in the solar industry. Steam condensate is recycled in all of these industries to help reduce the water sourcing costs as well as lessening the environmental impact of the power plants. By recycling water, less water is required, but also fewer chemicals are required to treat the water. So the cost of the water becomes a real motivating factor in recycling the condensate in the steam system and trying to be as efficient as we possibly can be in how we use that water and how we make the steam. Pulp and paper mills also use a tremendous amount of water and steam, making the industry probably the largest user of steam right after the power generation industry. Steam in pulp and paper is used to heat the pulp to break down the wood fibers with the addition of a variety of chemicals. But it ultimately, by breaking down the wood fibers, creates the paper that is a big, important part of our lives. In the textile industry, steam is used as a reliable to help make our processes more reliable and more efficient. Although in the textile world, primarily steam is used in drying type of applications. So we've been talking about the history of steam, where steam is used in industry, and we've seen how steam impacts us all in our daily lives, both at home and at work. So let's talk a little bit more about the steam itself. Here's where we get into the some of the technical terms, and I'll try to not be too overwhelming. Perhaps some of you listening today have had college level courses in thermodynamics, and you know quite a lot about what I'm going to talk about. But for the benefit of those who may not have had that background, when we talk about steam, we talk about its quality. Steam quality is a percentage number that expresses the dryness fraction of the steam. For instance, steam that has a 5% liquid has a steam quality of 95. And said a different way, you could say a zero quality factor is not steam at all, but just water. But steam with a quality of zero really has no industrial purpose other than it can be reheated and create higher quality steam once again. So basically, zero quality steam is just condensate. Maintaining high quality or high percentage steam carries quite a number of benefits, including the prevention of a range of pipe and valve issues that I'll discuss in a little bit more detail in just a little while. In heat transfer applications, low quality steam can reduce the rate of heat transfer by as much as 65%, just due to the difference in the energy level. So it's important to keep steam as hot as possible and keep its quality as high as possible. On this slide, you can see what's commonly called the steam saturation curve. It basically describes the line at which you transition from hot water to steam. Steam can exist at any pressure and temperature combination above the saturation curve, so just remember that above the line is steam, below the line is hot water. Putting more heat into the steam is called superheating the steam. So the amount of extra heat input above the saturation curve is the degree of superheat contained in that steam. If you look at the curve on this slide, you see that I've indicated an operating point at 180 degrees C, and also at a pressure of 2 megapascals gauge pressure. That operating point will have 47 degrees on the Celsius scale of superheat. Why do we want to superheat the steam? Very good question. Steam is considered to be 100% dry steam that has not been heated above the vaporization point at a given pressure. Superheated steam is 100% dry steam that has been heated to its vaporization point, sorry about that, at the same pressure. Steam managed properly, the steam condensate can cause considerable damage. Managed improperly, the steam condensate can cause a lot of damage to the steam system itself. So we have to be very careful about making sure that we're draining the condensate away and keeping it away from the parts of the system that that may be negatively impacted by condensate. Here I'm illustrating an example of saturated steam at 100 psi gauge, and that at that pressure it has a saturation temperature of 338 degrees Fahrenheit and a specific volume of 3.88 cubic feet per pound. Just as a footnote, specific volume is actually the inverse of density. So instead of talking about pounds per cubic feet, we're talking about cubic feet per pound. But if we increase the temperature to 400 degrees F, that's just 62 degrees Fahrenheit of superheating, the specific volume now increases from 3.88 to 4.93 cubic feet per pound. This allows that same number of pounds of steam to deliver more energy to the turbine or to the process, making electrical generation that much more efficient. Let's talk a little bit about some of the issues that we have to deal with in all of these different processes and all the different things that we want to do with steam in modern industry. Steam condensate issues are numerous. Many steam maintenance problems can be traced back to inadequate or improper condensate removal from the system. Other factors like low steam quality, unsuitable equipment and components, poor piping practices, undersized or oversized pipes and valves, all these play a role in some of the issues that we see in steam condensate systems today. Those issues can be corrosion, reverse flow, which means the steam is, or the condensate rather, is flowing in a direction we don't want it to flow. And what happens then is that steam condensate can then be heated and flashed back into steam. Condensate flashing can have several different problems associated with it all by itself. So we need to be very, very aware and very cognizant of the problems of collected steam condensate. There are many bad outcomes, as I said, by not managing steam condensate properly. Pipe failures can be catastrophic, like the ruptured underground pipeline you see in this slide, or they can be extreme. When the pipe fails, it could fly across a parking lot and land on the back of a pickup truck. And that's a picture of somebody's Chevrolet pickup that's had a big, heavy section of pipe land on it. It's hard not to overemphasize the importance of managing steam condensate because things can go wrong in a big hurry if you don't. Carbon dioxide in the pipeline can combine with the condensate and can lead to the formation of carbonic acid, which will corrode metals quite quickly, as you can see in some of these slides. These cross sections of pipes have been corroded by carbon dioxide and the resulting carbonic acid. Free oxygen in a system also will be highly corrosive on all the piping system components, particularly carbon steel, which is the most common material that's used in the piping systems, both for the pipes as well as the components, the valves, the flow meters, pumps, all generally carbon steel in nature. Areas where large quantities of condensate collect can be pushed by the flow of the steam, as you can see in the illustrations on the right-hand side of this slide. When that liquid then flashes to steam, tremendous forces are exerted that can destroy pipes, valves, heat exchangers, even the pipes themselves. In this slide, I'm illustrating just how a simple S-bend in the piping system with any elevation change, when all that's done in the wrong direction, can lead exactly to this condensate pooling problem that I'm talking about. And so the correct thing to do would be to locate a steam trap in that type of a section of piping geometry. The water has to be separated from the steam. There are many different types of steam traps that exist depending on specific applications. I'm showing just a few basic types in this slide. There is a float-style steam trap, a controlled disc steam trap, as well as bimetallic style steam traps. These are all commonly available varieties and types of steam traps. And I don't represent a company that makes steam traps, so I don't consider myself to be an expert on what's the best steam trap for the particular application. That expertise really should come from the steam trap manufacturers. In addition to the problems associated with steam condensate, there's also opportunities. And I'm showing you that condensation curve graph again on this slide to illustrate that high pressure condensate can be used to create lower pressure steam. So just above the curve, I'm showing the original operating conditions I'm describing by P1, T1. Thermal energy is lost due to the process, but the pressure remains the same. We're pretty nearly the same. So now we move from the operating pressure condition from P1, but a new lower temperature that I'm calling T2. If the system's operating pressure is reduced to the third point on the slide that I'm describing by P2 and T2, we've now moved back outside of that saturation curve and have gone to an area where we once again have steam instead of hot water. Sometimes this process is called flash steam, where you're flashing the steam in a controlled way to get to that lower energy, lower temperature, lower pressure steam that can be used to drive other processes, secondary type processes. Check valves can be very important in the process of steam condensate management. It's not always possible to use off-the-shelf valves for the applications for check valves in a steam or a condensate system. Oftentimes, low cracking pressure check valves are required. Typically, screwed-end check valves are the most common type used in these applications, but not the only type. We can also see flange-style and wafer-style check valves being used in condensate systems. It's a function of size. It's a function of where these valves are going to be located that might determine which of the three styles, screwed end, flanged end, or wafer style might be used. But what I'm emphasizing here are the low cracking pressure check valves that need to be specified for condensate lines. In normal steam lines or hot water lines, standard cracking pressures may be very sufficient, but there may be other special modifications needed to a standard valve to get the best performance of the valves in these applications. And in those situations, we may be thinking in terms of different seat materials, for instance, soft seats as opposed to metal seats. As I mentioned before, corrosion is a common concern in steam condensate systems. Particularly important when condensate is allowed to accumulate and sit stagnant within the system. Left untreated, over time, the corrosion can lead to system contamination, valve malfunctions, the bursting of pipes, and many, many other problems. Any of these events can lead to costly system shutdowns and huge emergency repair costs. I like to describe those as the phone calls that you get at 2 o'clock in the morning. We don't want those, and we want to avoid those 100% of the time, if that's at all possible. There are three different pressure spike scenarios that can occur in piping systems. The first occurs in liquid-only systems. These pressure spikes can be caused by valves closing suddenly or pumps shutting down suddenly. And they're typically only liquid-only systems where this might happen. In steam systems, condensate can accumulate and then flash to steam. As the steam expands to a vapor, its volume will increase by 500 to 600 times. That's an amazing amount of expansion. The third most dangerous form of water hammer also happens in steam systems and is commonly called condensate-induced water hammer, or CIWH, if you're into the acronyms. But this is when the pooled condensate is being pushed by the high velocities of steam traveling in the pipe. Much like the wind pushes the water on a pond or a lake, creating waves, it can do that also in a controlled, closed volume like a piping system. When the steam builds up a wave front in the pooled condensate, a flashing of the liquid from liquid to vapor can have very dramatic and very catastrophic consequences, because it will push that slug of water into an elbow or some other constriction at velocities in the hundreds of feet per second. You can see here on the illustrations, I'm looking at a big chunk of pavement that was blown out. That actually happened in New York City, I think 5 or 6 years ago. We're also looking at the broken valve in the piping system with the technician standing there in the lower photograph, and there's a big chunk of that wide pattern of that valve is gone as a result of this high-level explosion of steam. There are a number of factors that should be carefully considered when designing or redesigning a steam condensate system. These include line sizing, and I focus a lot in this webinar and other webinars that I've done on the value and importance of properly sizing the lines and the valves that are in that system. And I do mean all of the valves. Always make sure that the pipes themselves are properly sized, because this can be a leading cause of steam condensate collection. The location of condensate return lines in relation to other pieces of process equipment is very, very important. Installation methods and techniques are particularly important to prevent flashing. Look for low points where condensate can and will accumulate. The final point I want to leave you with in this slide is to consider the type or quality of the valve used, particularly check valves. Not all check valves will do an adequate job of handling condensate. Again, there may be special modifications to the valve required for low cracking pressure springs. Perhaps even a soft seat material would be advisable to prevent steam from wire drawing and creating an erosion, if you will, between the closure mechanism and the seat mechanism. So what have we learned today? Well, I guess beauty is in the eye of the beholder, but then knowledge is in the head of the individual. I would say that we've definitely learned that steam itself, of course, plays an important role in just about every industrial segment we can think of. Chemical processing, mining, petroleum production, petroleum refining, power generation, pulp and paper, textile. These are all just some of the industries that use steam every day to do what they need to do to provide the service or the products that we're looking for. Maintaining high-quality steam carries a number of benefits, including the prevention of a range of piping and valve issues. Proper system designs are inherently lower in maintenance costs. Recovering steam condensate saves the user money, but can also be a source of low-pressure steam. That flash steam that I talked about a few slides back can be used in other parts of the process as well. DFT Incorporated has been designing and manufacturing world-class inline silent or non-slam check valves since 1943. When check valves are sized properly for the system, you get a higher integrity of the system, and critical components of your steam condensate system will work a whole lot better. One of the most popular valves that we sell into steam condensate is our SCV check valve. This is the screwed end style check valve that you see in the illustration of this slide. The valve style, coupled with some simple modifications for low cracking pressures, performs exceptionally well in many steam condensate lines. And there are a lot of other options that may be worth considering. We suggest that you contact one of our valve experts at DFT with your problems and discuss the specific issues that concern you. We have other resources available to help you solve many of your valving and piping problems, and I'd like you to look up some of those resources about water hammer, about the challenges of steam and condensate, and review our ebook that's available through our website below. And look, when you go to our website, look under the literature tab, and you'll see the link there. If you sent me any questions, I will be very happy to answer them after this webinar. As I said, I will be responding to your emails with an email, and I will try to provide you with all the information you need and answer your questions. Please feel free to contact me through our webpage or through any of our regional sales managers or marketing people. Thank you for being a part of this webinar today. I really do appreciate your attendance and look forward to the questions that you may have for me, and I will answer them immediately after this webinar concludes. Once again, thank you very much, and I appreciate your attendance today.